Hello students, welcome to our YouTube channel Experience Tutor. Today we'll discuss Class 12th Physics, Alternating Current, Chapter 7, ncert, Line by Line, Part 2. This is one more lesson in the series of Get More Than 95% Marks. Before we begin, we request you to subscribe our channel Experience Tutor if you have not done yet. Please like and share our videos among your friends and relatives. Please click on the bell notification so that you can get automatic notification whenever a new video is uploaded by us so that you will not miss any of our videos and important lessons. Let us begin today's class. Today we'll start with 7.4 AC voltage applied to an inductor. Now, for this, first see this diagram. In this diagram, you can see that an AC source is connected to an inductor. Usually, inductors have appreciable resistance in their windings, but we shall assume that this inductor has negligible resistance. Thus, the circuit is purely inductive AC circuit. Let the voltage across the source be V is equal to Vm sine omega t. Okay. Now, what we'll do, we'll solve it in very easy way so that you won't have any problem to understand. Now, so already you have seen the circuit. So now if you want to draw it, just draw a circuit here with an AC source and inductor. Now we can write the potential difference V is equal to Vm sine omega t. Next, by Kirchhoff's law, we can write is equal to 0. So Kirchhoff's law. Kirchhoff's law sigma E is equal to 0. E is the EMF or potential difference. So we can write V minus L di by dt is equal to 0. What is this second term for? This second term is the self-induced EMF by Faraday's EMF in the conductor. So it is induced EMF. Induced EMF. L is the self-inductance and L is the self-inductance. L is the self-inductance of the inductor. Now, the negative sign, the negative sign is due to the Lenz's law, came from Lenz's law. So this negative sign is from Lenz's law. That's it. So everything is explained. L is the self-inductance of the inductor, and di by dt, L di by dt is the induced EMF, which according to Faraday's law, and this negative sign is given by Lenz's law. Now we can write the following. Di by dt is equal to V upon L. We know that di by dt is equal to V by L. So instead of V, we can write Vm sine omega t upon L. This is equation 7.11. Now, if we integrate, so what we do, di by dt, we multiply the equation 7.11 by dt in both the side, in LHS as well as in RHS dt. On both sides we multiplied by dt, and after multiplying, what we did, we put integrating both the sides, so Vm by VL is constant. So okay, integrating both the sides. So two steps we have done. First, multiplied dt both the side, or whole equation we have multiplied by dt, and then integrating both the sides. So what we get here, we get integration of di, and here we get Vm by L is constant. So it is out of integration, and sine integration of sine omega t dt. Now by solving it, we get I, integration of di is equal to I Vm by L, then sine integration is, sine omega t's integration is minus cos omega t, and omega t's integration is 1 by omega. Upon solving, we get I is equal to Vm L omega upon L omega. Cos and minus sign is here, cos omega t, plus a constant that is called integration constant. Now instead of minus cos omega t, we can write, by the law of trigonometry, we can write sine omega t minus pi by 2. So this equation can be written as Im. Instead of minus cos omega t, we will write, instead of this whole value, we have written Im. Instead of minus cos omega t, we have written this value, Im sine omega t minus pi by 2. So this can be written as 7.2. This is written as 7.12 in your book. And Im is written as Vm upon omega L. And it is the amplitude of the current, which is equal to the amplitude of the current. Omega L. Omega L is the quantity which is analogous to the resistance, and it is called inductive reactance. And this is denoted by X, capital X L. Therefore, we can write XL is equal to omega L. This is denoted by 7.13 equation number. Amplitude of the current is then, so amplitude of the current Im is then Vm by XL, which is written as 7.14 in your book. From where we get this? From here we get this. Im instead of Vm, and instead of omega L we have written XL. Let us see this derivation from the beginning. So we have drawn a circuit of AC current which is connected to a inductor L. So we can write V is equal to Vm sine omega t. By Kirchhoff's law, sigma EMF E is equal to 0. So we can write V minus L di by dt. V minus L di by dt is equal to 0. The second term is the induced EMF uh, given by Faraday's law, and L is the self-inductance. Uh, L is the self-inductance. Now, what we have done, di by dt is equal to V by L. We know that di by dt is equal to V by L. So, instead of V, we have written Vm sine omega t by L. So, di by dt is equal to Vm sine omega t by L. This is equation 7.11. Now, what we have done, we have multiplied the whole equation by dt and integrated both the side. And integrating both the side, what we get? Integration of di Vm by L, integration of sine omega t dt. So integration of di is equal to I and Vm by L multiplied by sine omega t dt's integration is minus cos omega t, and cos omega t's integration is uh, omega t's integration is 1 by omega. So ultimately we got Vm by L omega minus cos omega t. And next, upon solving, I is equal to minus Vm L omega cos omega t plus integration constant. So now minus cos omega can be written as sine omega t minus pi by 2. Then we have written minus cos omega t as sine omega t minus pi by 2, and so the equation became I is equal to Im sine omega t minus pi by 2. This is equation number 7.12, and Im is equal to, where Im is equal to Vm by L omega. So here we have considered here this value as Im. We have considered this whole value as Im. So Im is equal to Vm by L omega, which is equal to magnitude of the current, amplitude of the current, which is equal to amplitude of the current. Omega L is also called inductive resistance, which is which can be written as XL. So XL is equal to omega L. Therefore, Im can be written as Vm upon XL, which is equation number 7.14 in your book. Now let us see the book. So we have already seen how 7.14 came. Im is equal to Vm XL. The dimension of inductive resistance is same as that of resistance, and so dimension of inductive resistance is same as that of resistance, and its SI unit is ohm. The inductive resistance limits the current in a purely inductive circuit. So inductive resistance limits the current in a purely inductive circuit in the same way as resistance limits the current in a purely resistive circuit. The inductive resistance is directly proportional. It is directly proportional to the inductance, to the frequency of the current. A comparison equation 7.1 and 7.12 for the source voltage and the current in the inductor shows that current lags the voltage by pi by 2 or 1 quarter 1 by 4 cycle. Figure 7.6a shows the voltage and the current phasors in the present case of at instant t1. The current phasor I is pi by 2 behind the voltage phasor V. So the current phasor I is pi by 2 behind, then the voltage phasor V. When rotated with frequency omega counterclockwise, they generate the voltage and the current given by equation 7.1 and 7.12 respectively, and shown as figure 7.6b. So let us check 7.6b, the figure. So this is the figure here. So of figure A shows the phasor diagram of the circuit in figure 7.5. B shows the graph of V versus V and I versus omega t. So just check this figure. So from figure B we understand that that the current phasor I is pi by 2 behind the voltage phasor V. in this way. This angle is pi by 2. This difference is pi by 2. Again, this difference is pi by 2 from here to here. Again, this difference is pi by 2. Now, if we want to find out the instantaneous power supply of the inductor, then PL is equal to, we can write I into V. I we can write as Im sine omega t minus pi by 2 multiply by Vm sine omega t. V, instead of V we have written this, instead of I we have written this. Now upon solving we can write minus Im Vm cos omega t sine omega t. How we got this? So instead of sine omega t minus pi by 2 we can write minus cos, and rest Vm we have coupled up with Im and Vm because it is whole are multiplied, so we can rearrange according to the question. So what we do now, I will multiply and divide by 2, and we can write sine omega t cos omega t. This whole equation can be written as I minus I sine omega t sine omega t upon 2. So here we have missed something. Let us correct it. So minus Im Vm. We forget to write. Now same Im Vm minus Im Vm sine omega t upon 2. So the average power over the complete cycle. So average power we can write PL average we can write as average minus Im Vm upon 2 sine 2 omega t and mean. So we can write it minus Im Vm upon 2 mean value of sine 2 omega t mean value is closed is equal to 0. And we came to this expression. Now the average power supplied to an inductor over a complete cycle is 0. This means the average power supplied to an inductor over a complete cycle is 0. So PL average is 0. Thus the average power supplied to an inductor over a complete cycle is 0. Now let us see few of the examples. So we got this equation. Finally, we have reached to this equation, and since the average of sine omega t over a complete cycle is 0, thus the average power supplied to an inductor over a complete cycle is 0. Now Let us see the examples based on this concept. A pure inductor of 25 mH is connected to a source of 220 volt. Find the inductive resistance and RMS current. So inductive reactance and RMS current in the circuit if the frequency of the source is 50 Hz. So the inductive resistance XL is equal to 2 pi nu L. 2 pi nu L. So put the value 2 pi nu is 50 Hz given and L is 25 mH. So 25 into 10 to the power minus 3, the minus 3 we have written, we have converted and to SI unit, and the and upon solving we got 7.85 ohm. The RMS current in the circuit I is equal to V by XL. So we have got the value of XL as 7.85 ohm and V we know 220 volt, which is already given in the question. So we got 28 ampere I. Now we'll do few physics concepts based on this chapter, AC current. In this figure, what we can see, current I through the coil entering at A increase from 0 to maximum value. The flux line are set up, that is the core gets magnetized with the polarity shown. Voltage and current are both positive, so their product P is positive. Energy is absorbed from the source. In this case, energy is absorbed from the source. In the other case, current in the coil is still positive but is decreasing. Here, the coil gets demagnetized and the net flux becomes zero at the end of the half cycle. The voltage V is negative, that is di by dt is negative. The product of voltage and current is negative and the energy is being returned to the source. So these are the two opposite conditions which just you remember. Here this figure shows a complete cycle of voltage oblique current. Note that the current lags the voltage. Now the next concept here, current I becomes negative, it enters at B and comes out of A. Since the direction of the current is changed, the polarity of the magnet changes. The current and voltage are both negative, so their product P is positive. Energy is absorbed in this case. In this figure, current I is decreases and reaches to 0 value at 4 when cores are demagnetized and flux is 0. The voltage is positive, the current is negative. The power is therefore negative. Energy absorbed during 1/4 of cycle 2 by 3 is returned to the source. In this case, 2/3 is returned to the source. So section 7.5 AC voltage applied to a capacitor, will do it in the next class. Now today we recapitulate what we have done. Today we have started with section 7.4 AC voltage applied to an inductor, and we have done few of the derivations and explained separately from the book We have found the value of mean mean value of or average value of power. We have seen the graphs related to it, and we have solved few of the numericals. We have seen few of the cases and where energy is absorbed from the source and where uh, the current is passing through the coil and magnetizing the core, and where it is demagnetizing the core, and few of the related graphs. And that's it. So in the next class we'll go through the section 7.5, AC voltage applied to a capacitor. We request you, before closing our class, please subscribe our channel if you have not done yet. Please like and share our YouTube channel and videos among your friends and relatives. Please click on the bell icon so that you can get automatic notification whenever a new video is applied and uploaded, so that you will not miss any of our important videos and updates. Thank you very much for your support and watching our videos.